All right, everyone. In this video, we are going to continue our exploration of series with an eye towards whether or not series converge or diverge, and when we can conclude definitively that a series might converge. This video is going to be all about series with positive terms. And what I mean by that is that we will be looking at series of the following form: a sum as n goes from 1 to infinity of a sub n, where the individual terms a sub n are all greater than 0, are all positive. So we'll save any conversation with negative terms or sort of like a plus minus situation for a future video. Today, everything that we add up in our series is going to be positive. We're going to begin with arguably the most important example of a series up until this point. And this is one that we'll always want to keep in the back of our mind as a potential example of interest. This is the so-called harmonic series. And so our harmonic series is a series of the form sum as n goes from 1 to infinity 1 over n. And so we can see the first bunch of terms written out on this page. Starting at 1, we get 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on and so on and so on. We note here that this is not a geometric series because there's not a common ratio. And so it is a brand new series that we're looking at. You'll note that the individual terms trend towards 0. So we go 100 terms out, we're at 1 over 100. We go even further out, we're at 1 over a million or 1 over a billion. Those terms are getting very, very, very small. And we might be led to conclude falsely that the harmonic series probably converges. We would be wrong in that case. And it's that counterintuitive result that makes the harmonic series so important and so interesting. And so let me be upfront in saying the harmonic series diverges. And I personally feel like that is a surprising result until you see an argument for why that is true. So we will actually see two different arguments in this video. The first we'll see right now. So the harmonic series is the sum that we see written here. And I just want to point out that when we start adding these terms together, we're going to get the following result on our sequence of partial sums. So of course, the first number is just 1. So that's pretty big. The next number is just going to be 1/2. But now take a look at this. If I add the next two numbers together, a third plus a fourth, I want to point out that this in total is greater than a fourth plus a fourth, right? Because a third is bigger than a fourth. So 1/3 plus 1/4 is a greater quantity than a fourth plus a fourth. And a fourth plus a fourth is, of course, just 1/2. So if we just look up to our fourth partial sum, we've got 1 plus a half plus a third plus a fourth. We know that the fourth partial sum, what we might have written as s sub 4 previously, is going to be bigger than 1 plus a half plus a half. So it's going to be bigger than 2. Now, let's look at the next four terms all together. So a fifth plus a sixth plus a seventh plus an eighth. Notice that this is greater than an eighth plus an eighth plus an eighth plus an eighth. Because again, each of those individual numbers is bigger than 1/8. And therefore, the sum of those four terms is bigger than 4/8. So it is again bigger than 1/2. And therefore, the sum of the first 8 terms, 1 plus a half, plus a third plus a fourth, plus a fifth, sixth, seventh, and eighth, is all told greater than 1 plus a half, plus a half, plus a half. So it's greater than 2.5. And maybe you can start to see where this is going. If we take the next 8 terms, so starting at 1/9 and going up to 1/16, that will be greater than a 16th plus a 16th plus ... 8 different times, that will be greater than 8/16, which is again 1/2. And so therefore, s sub 16 will be greater than 3. We add up the next, in this case, 16 terms. That will be bigger than 1/2. We add up the next 32 terms. That will be bigger than 1/2. And so on, and so on, and so on. So as we look at our sequence of partial sums, we see that it is monotone, but it is not bounded, right? S sub 32 will be bigger than 3.5. S sub 64 will be bigger than 4, and so on and so on. And this series will just creep up and up and up and up. So because the sequence of partial sums does not converge, we say that the series does not converge. And again, therefore, the harmonic series as a series diverges. Now, this, I think, underscores the challenge of looking at series with even all positive terms. So in this situation, we get a series that looks like, or at least maybe at first glance, we could have believed converges, but now we have an argument that says that it does diverge. So this is a sign that we should proceed very carefully in trying to understand when a series converges and when a series diverges. All right, so with all of that, we're going to look at 3 major examples or results here going forward. The first is a specific type of series called a p-series. Now, a p-series is just a series that is in the form written here. It is a sum of a bunch of terms, all of the form n to the p. So looking at a specific example, we could say, let's take p equals 2. So this is a p-series with p equals 2. And this would be the sum of expressions of the form 1 over n squared. So this would be like 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on and so on. So this is an example of a p-series, and we can create a p-series for any potential power p. So I will claim this as a fact, although we can prove it down the road, that we actually have a robust understanding of when our p-series converge and diverge. So a p-series will converge whenever our p-value is greater than 1, so whenever our power is greater than 1, and a p-series diverges if p is less than or equal to 1. So the example that I've written right here, the p-series with p equals 2, this converges. And it converges because it is a p-series where p is equal to 2, and specifically greater than 1. As another example, the harmonic series that we just listed diverges according to this fact. So the harmonic series, that's 1 over n, aka 1 over n to the 1. This diverges because it's the harmonic series, and we already showed this. But in this case, we can say it diverges because it is a p-series, and p is equal to 1. So we're in that second camp. All right, and so those are our p-series. Now, let's take a look, based on the p-series, or I should say stemming off of the p-series, let's go on and take a look at something that we call the integral test. So the integral test is another way to check and see if a series converges or diverges. And the statement of the integral test, which I'll read here for you, is as follows. First, we look at our series, and specifically the terms in the series, the a sub n, and we identify that sequence of a sub n values with a function f of x, specifically identifying the a sub n value with f of n. So in the example that we're going to look at, again, we're going to stick with the harmonic series. In the harmonic series, our sequence was 1 over n. And so we're identifying that with the function f of x equals 1 over x. Now, the integral test says if we do this, identifying our sequence of terms with a given function, and if that function is positive and decreasing and continuous, then the series a sub n converges if and only if the improper integral of f of x also converges. So the series will converge if the integral converges, and the series will diverge if the integral diverges. And so let's take a look. We're again comparing the series of 1 over n now with the function 1 over x. And the function 1 over x is a positive function. It is decreasing, and it is continuous. So according to our understanding, or according to the integral test, the series a sub n, or let me say the series 1 over n, converges if and only if this improper integral converges. Right? But as a reminder, to check that, let me finish this thought. We have to check and see whether that converges. So to check and see whether that converges, what we need to do is set up an integral from 1 to b, and then take the limit as b goes to infinity. So that's how we take an improper integral. We take a proper integral, letting b go to infinity. And now, as a reminder, I'll keep that limit out front. The integral of 1 over x is ln of x, evaluated from 1 to b. So this is the limit as b goes to infinity, and this is ln of b minus ln of 1. Now, ln of 1 is just 0, so that last piece goes away, but the limit as b goes to infinity of ln of b is itself equal to infinity. The ln function just keeps growing and growing and growing. And so what can we say? In this case, we are forced to conclude that the improper integral diverged. I'll draw the conclusion down here at the bottom. The improper integral diverged, and so our series, which again is the harmonic series, must also diverge. And now we've seen 3 different arguments for why our harmonic series diverges. Our original argument, which was right up here, and then recognizing the harmonic series as a p series in the divergent case of p less than or equal to 1. And then finally, using this integral test. I will mention that we can actually use the integral test to prove that our p series rule up above holds true. So what I previously called a fact is something we can rigorously prove using the integral test. All right, and now I want to conclude this video by discussing one more kind of test, the comparison test. The comparison test allows us to compare 2 different series under certain conditions and try to conclude that just because one of them converges, the other one converges as well, or just because one diverges, the other diverges. So in our comparison test, we are asked to assume we're looking at 2 series, a sub n and b sub n. Each of them are in this situation with positive terms. And we're also going to assume that the individual terms, a sub n, are always less than or equal to the corresponding term, b sub n. Right? So this is a term-wise inequality. It means the first term of the a's is smaller than the first term of the b's. The second term of the a's is smaller than the second term of the b's, and so on. Under this framework, we can conclude the following two results. If the larger series converges, so this B sub n series converges, we can conclude that the smaller series also converges. And vice versa, if the smaller series diverges, the larger series must also diverge. So the comparison test lets us look at a weirder new series by comparing it to a series we already know. And in the example here, we're looking at our new stranger series, 1 over n squared plus 1, and we are comparing it to a better understood series, 1 over n squared. Notice in this framework, 1 over n squared is, I wrote it in the wrong spot. Let me try that again. 1 over n squared is playing the role of our larger series. That is because individual term-by-term comparison shows us that 1 over n squared is larger than 1 over n squared plus 1. Notice the n squared plus 1 is the larger denominator. They both have the same numerator, and so the larger denominator results in a smaller number. As an immediate comparison, notice that the first term is 1 over 1 squared plus 1. That is smaller than just 1 over 1 squared. So we can see that's true in the first term. And we can also see that's true for all future terms. Because we have this result, we can now turn to the series we know better, the 1 over n squared, and check that one. In this case, 1 over n squared does converge, and it converges because it is a p series with p equals 2. Because it is a p series with p equals 2, we know that it converges by our p series fact up above. And because the larger series converges in this case, the comparison test lets us conclude that the smaller series will converge as well. And so we can say that 1 over n squared plus 1 also converges. And this is just in a direct comparison to what it's above. All right, so this gives us a few new tools in our toolkit, allowing us to examine series with positive terms. We can look to see if it is a geometric series or a p-series, and if it's either case, directly draw a comparison, or I'm sorry, directly draw a conclusion about whether or not it converges. Or in more complicated settings, we can use the integral test or the comparison tests to look at our more complicated series and either try to integrate it or compare it to a simpler series. That's going to do it for this video. Thanks so much for watching. See you next time.